I'm guessing it's stuck. Okay, sorry. Gravity storm came in and wiped out the camera, so we're back again. Okay, so back to force and acceleration. So I can pull it down a little bit farther, okay, right? And then I can pull it farther. And then if I go all the way down to the bottom, okay, it flies all the way up, okay? So I have two variables here. I have force and I have the acceleration of the marble, right? So which one of those is my independent variable? Force or acceleration?
Force.
Why?
Because that's the thing you're changing.
Yeah, I can control how much force I apply, right? So this is my independent variable, and that's my dependent variable. So if I were to graph this, I'd have force here, and then acceleration here. Now, actually, you'll see why I'm going to do this in just a second. Okay? So, I'm going to put acceleration here in meters per second squared. And then I'm going to put force here, and I'm going to put this as kilograms meters per second squared. And you'll see why in just a second. So, here's the million-dollar question. Well, this graph started at the point 0, 0.
Yeah, I'm gonna say yeah.
Yes, why?
If you don't put any force on it, it's not gonna move.
Yeah, Mother Nature is a lazy prima donna, right? If there's no force applied, you're not going to get an acceleration. So I know for certain that this graph is going to start at 0, 0. Okay, so I know this is going to be one of my points. Now, think about this. As I apply more and more force, what happens to the acceleration of the marble?
It's higher and harder.
Right? Because the harder you hit something, the more acceleration that you get. So this graph is going to go something like this. I know it's going to start at 0, 0, and then it's going to go up like this. So I know that's what's going to happen. Right? Now, here's the deal. And this happens when you all drive. Okay? If you just barely press down on your gas pedal, you don't get very much acceleration. If you really press down on your gas pedal and apply a lot more force, you get a bigger acceleration. And the same thing is true when you hit the brakes on your car. Okay? If you barely tap the brakes on your car, hey, you just slow down a little bit. You don't get much of an acceleration. A little squirrel runs out, and you like squirrels, okay? And so you want to stop, right? So you're really going to slam on the brakes, and your car is going to come to a stop. So this is true whether you're speeding up or slowing down, doesn't make any difference. Here's the main idea. The more force that you apply, the bigger the acceleration is. So if you look at this in terms of data, so let's say that I know that this point out here is, say, 1 Newton, and I know this point over here is, say, 10 meters per second squared. Okay, I'm just making up some numbers. So I know this is 1 Newton of force, and I know this is 10 meters per second squared. Now, I know my other data point is 0, 0. So here's the million-dollar question. At this point, could I find the slope of the line? Do I have enough information up here to find the slope of that line?
Yeah.
Yeah, I've got 2 data points, right? I've got 0, 0, and I've got 1 and 10. Okay? So let's find the slope of the line. Now, if you're in a math class, okay, you can go, oh, change in y over change in x, and you can go, oh, change in y That's going to be 10, and I'm going to do this wrong. Do not do what I'm about to do. And then I'm going to have my force of 1 Newton, right, minus 0. And I would say my slope is 10. Okay? Now, in a math class, that's all you'd have to do. Put in the numbers. The slope doesn't have any physical meaning. But in a physics class, you have to pay attention to what those units are. So now, I'm going to come in here and do it like I want it done in a physics situation. So now I'm going to take 10 meters per second squared minus 0 meters per second squared. Now, instead of newtons, I'm going to put in kilograms meters per second squared. Okay? Now, for now, I know I'm still going to get an answer of 10, but now I want to pay attention in this whole process of dimensional analysis. And I want to see what's going to happen here. So, you know, when we go through this process of dimensional analysis, it's tough for me, for you guys, to get you guys to buy into it, because you all are just used to taking numbers, putting them into a calculator, getting an answer and writing down, in this case, 10. Okay? That's what you all are really good at. But the sooner you embrace this idea of dimensional analysis and paying attention to the units as you go along, the deeper your understanding of this class is going to be. Okay? Because I promise you, no one is going to pay you $60,000 a year to crunch numbers into a calculator and write down the number 10. Okay? It's not going to happen. They're going to expect you to know what that number 10 represents. Okay? And the sooner you embrace this idea of paying attention to the units, the better off you're going to be. So, here's what we're going to do. So, just in terms of dimensional analysis, don't worry about the numbers for now. So up at the top I had meters per second squared, and then on the bottom I had kilograms meters per second squared. So in this situation, the meters per second squared cancels out, and I'm left with 1 over kilograms. Notice that it's not kilograms, okay? That is a huge, huge thing to understand. That is not kilograms, okay? It is not kilograms. It is not kilograms. So what this is 1 over kilograms. Now, for now, I want you to pretend that that's gone, okay? Don't worry about it. We'll get back to it. We'll get back to it, okay? For now, I want you to pretend that you're in a math class. I want to talk about x, okay? It's a variable, x, I don't know what it is, it's just x. And if I said, okay, I want you all to write the inverse of x. So what's the inverse of x?
1 over x.
1 over x. Or you could write it as, what's the other way to write 1 over x?
Negative x.
X to the negative 1, right?
Yeah.
Okay? So both of these are inverses of x. Okay? Both of these are inverses of x. So, with that in mind, I want to come up here and we're going to play the what if game. Okay? So, if, okay, it wasn't, okay, it wasn't, it was not, listen to me, it was not kilograms. But if it had been kilograms, we would say the slope of the line represented the mass of the object. Okay? So if it had worked out to be like 10 kilograms, okay, it wasn't, okay, this is huge. It's not 10 kilograms. All I'm saying is if it had been 10 kilograms, the slope would represent mass. Okay? Now, but it isn't measured in kilograms. What it's measured in is 1 over kilograms. So just like x to the negative 1 or 1 over x is the inverse of x, guess what? 1 over kilograms represents the inverse of mass. Okay? So in this situation, If I ask you, what does the slope of the line represent? You would say the slope of the line represents the inverse of mass. If it had been kilograms, you would say it represented mass. If it was meters per second, let's say the slope had worked out to be meters per second, you would say, oh, the slope represents velocity. If the slope had worked out to be seconds over meters, you would say, oh, it represents the inverse of velocity. But here's the point. You'll never know what these values, what that slope represents until you begin to pay attention to the units. Okay? Now, the other thing we want to do is we want to play the what if game. Okay? And if you're, that's the whole nature of science, is you ask yourself, hey, what if we change this? So, I want to take a marble launcher, okay? But instead of using this small little plastic marble, I'm going to use this really dense steel marble, okay? Same volume, okay? There's a lot more mass in there. So now, I'm going to apply that force, okay? But now, whoop, when I apply that same amount of force, what happens to the acceleration of the marble?
Not as high.
Okay? You don't get as much acceleration, right? So here I'm launching this massive steel marble versus this small little plastic marble. Now, this is a reflection of what we call inertia, right? So inertia is the resistance to a change in your velocity. So basically, this plastic marble, it doesn't have as much stuff that wants to remain at rest, so it accelerates quicker. This has a lot more stuff that wants to remain at rest, therefore you don't get as much acceleration. Okay? Accelerates quickly, not as much with the same amount of force. So here's the deal. If you were to graph this, so if this is the plastic marble line, okay, what would happen to the steel marble line? So if I apply that, I'm going to apply that same force to this steel marble. What's going to happen to that acceleration? It's either going to get more acceleration, the same acceleration, or less acceleration.
Less.
Less, there's more stuff, right? So if that's the case, if I come in here and I draw this line, so if that's the plastic marble line, this would be the steel line. For the same amount of force, I'm not going to get as much acceleration. So with that said, that might be 5 meters per second squared. Now, here's what we're going to do. Okay? Now, this is where you take this all the way through. Okay? So, on the plastic marble line, we had 10 meters per second squared minus 0 divided by 1 kilogram meters per second squared. We got 10, 1 over kilograms. On the steel line, let's say we got 5 meters per second squared minus 0 divided by that same amount of force. Whoop, come back here. And I get 5, 1 over kilograms. Now, this is where you take this through to like the next level of thought, okay? So, if this, think this through. This represents the inverse of mass, right? Okay, represents the inverse of mass. So, think, this is going to get a little bit confusing, but think this through. If this represents the inverse of mass, if I were to take the inverse of mass, what do you think I would get?
Mass.
I'd get mass. So, look, this is where the magic happens. If I were to take the inverse of this number, if I take 1 over 10 and then 1 over kilograms, if first off, the kilograms are in the denominator of the denominator, so the kilograms would flip up, and I would go, oh, the actual mass of the object is 0.1 kilograms. Now, if I take 1 over 5, 1 over kilograms, I get 0.2 kilograms. So notice that this, the actual mass of the object here, is bigger than this mass here, okay? But the slopes, okay, because we plotted, what we actually plotted was force and acceleration. So the steel marble has a smaller slope, but it actually has a bigger mass. The plastic marble has a bigger slope, but it actually has a smaller mass when you take the inverse of it. So on the test, I'm not going to, I'm not going to expect you to get to this level. I'm going to expect you to be able to draw a force and acceleration graph. But if you really want a deeper understanding of it, that's what you got to be able to do. Now, we can do the same thing with this little contraption here. It's kind of cool. Use that. So this is just a fan, okay? Got a little fan that sits in there and goes, and it's got 2 speeds. Trying to get this back. And then you go like warp speed, right? Okay. So I got 2 different settings. So yeah, you guys can see that. So I'm going to take this, and we're going to use these cards a lot, okay? So I got this, so I'm going to put this on here. I'm going to put it on a low. And let go of it. And we get a certain amount of acceleration, right? Now, if I double that speed and let go of it, I get more acceleration. So even with that, what I'm showing is that when you plot force and acceleration, the more force that you apply, the more acceleration that you're going to get. Now, if I do this, and I put a ½ kilogram mass on here, and I turn it on, now I'm increased the mass of the system. So what's going to happen to the acceleration? The acceleration should go down. So now when I do this, okay, I can get it to move, but not as much. But the same thing applies though. When I put it up on warp speed, I still get a bigger acceleration, but it's just not as much acceleration. So I can use a spring to cause the acceleration. I can use a fan. Later on in labs, we're going to do a string, and we're going to let gravity do that. Okay, I got some stuff to hand out. Stop that filming for a second, and then you all